Right, so our next chapter is to do with vectors. We've looked at these at National 5, but we're going on to introduce some new concepts with vectors. But before we start, just a wee reminder of what a vector is. So a vector is a quantity that has both magnitude and direction. Okay, so for those of you who do physics, you'll be well aware of vectors. For those of you who don't, you might be a little bit less aware, but like vectors, examples of vectors are velocity, displacement, acceleration, force. It's quite a few things that like the direction in which they happen is important rather than just what happens. So like speed is a scalar, which means it doesn't have a direction, it's just got a size. But velocity is the vector equivalent, which has to have a direction as well. Okay, so we can represent vectors by like a straight line, which illustrates its magnitude and its direction. So if we've got a straight line, excuse me here, I can't really use a ruler, it's close. Right, so we have the points A and B. If I draw a little kind of arrow like that, it gives us a vector. And there's two different ways that we can denote this. The arrow tells us the direction we're going, so we're going from A to B. So we can call it vector AB, and that line on the top is the way of denoting that it's a vector if we're using the points. Or we could give the vector a letter, which has a wee kind of line underneath it. And that's another way of denoting the vector. If we were going to go the other way, so from B to A, so B to A, it's the same as negative A to B, because we're just kind of reversing it, so it's going the negative version, so the same as negative U. So if we were to, they're exactly equal in magnitude, but they're opposite in direction, and that's where the negative comes in. Right, okay, so if we're talking about two-dimensional vectors, we have 2 dimensions and 3 dimensions. We'll go through 2-dimensional first. Right, so if I've got that same vector, let's call it U, and it's in some coordinate system, because it's in 2 dimensions, it's in an XY coordinate system. And we've got that length there, that's A, and that one that's B. So far, the way we've been able to show how we would write this is that U is equal to A, B, and that's component form of a vector. Okay, so, but if we wanted to find the negative vector of that, it's just negative A, negative B. Okay, and the last thing we need to be able to do with the 2-dimensional vectors is find the magnitude. We find the magnitude by writing the 2 straight lines on either side. That's how we denote that it means magnitude. So that's just the size of the line, and we do that using Pythagoras. You don't have to, you can either remember the formula or remember that it's Pythagoras. So it's the square root of a squared plus b squared because we're finding the hypotenuse. Right, so 3 dimensions. Things become a little bit harder to kind of draw and to visualize. But if we've got a vector u, again, it's going to have gone some direction in an A, and then it'll have gone some direction in a B, and then it'll have gone some direction, I'm going to extend this to make it work, in a C direction. And we have, this is a right angle in there, between A and B. And there's a right angle in between B and C as well. Right, I know it doesn't visually kind of make sense, but we've just got those three dimensions. So if we've got 3 dimensions, our vector is denoted as A, B, C, assuming that our axes are that our x direction's like that, our y direction's the one going backwards, and our z direction's the one coming up on that diagram. Right, so it's the same. The negative of the vector is just equal to like negative A, negative B, negative C. That's the component form. And the magnitude of this vector, it's similar to the other one, but just this time instead of having 2 terms, you've got 3. So it's the magnitude of A squared plus B squared plus C squared. Okay, right, so we'll be going on to a little bit more about vectors. Again, just a wee reminder. Right, okay, so when we are adding our vectors together, it's like saying if we're going to go from here, that's u, and if we've got a vector v like that, we can add those 2 vectors together, and what that actually gives us is the third side of that triangle. So that's u plus v. Okay, so that works. You have to make sure that the vectors are nose to tail, and what that means is that you've got, like, on your path that you're adding, you have a continuous journey, like unbroken arrows. So you can see if I start at the start of u, I can kind of follow all the way along u in the direction of the arrow, and then I can follow all the way along v in the direction of the arrow until I get to the end of the point that's the vector that's the sum of the 2. If you've got a negative, like if you've got 2 vectors that are in wrong directions, you just make it the negative. Okay, so the big thing when adding vectors geometrically, so that means like in a drawing, they need to be nose to tail. So that means like the end of one to the start of the other one. Okay, obviously we can't really draw them like that in 3 dimensions, right? But when we're adding and subtracting vectors using column vectors, so adding and subtracting using column vectors, what we do, it's really simple. What we are going to do is, so if we have a vector u, like the one there, which we're going to call AB, and we've got a vector v, which is going to be CD. If we want to find u plus v, all we have to do, so it's AB plus CD, and all we need to do is we need to add the top 2, A plus C, and then the bottom, add the bottom 2, B plus D. It's the same for subtracting, except obviously you subtract them, you don't add them. And in 3 dimensions, all that changes is that you've got a Z. It's exactly the same, so you just add or subtract the 2 Z's depending on what you want to do. Okay, so the other thing we need to be able to do is multiplying a vector by a scalar. And this is just like, so if I wanted to find 3u using the same u as I've got up there, that's just like doing u plus u plus u. And kind of a way to do that would be to do, it's like just 3a, 3 b. So you have to multiply kind of both bits by 3. That works for any of them. You can increase any vector by any size you wish, including fractions. You can't really increase it by 0, that's the only thing. If you're multiplying it by any number greater than 0, it'll multiply in the same direction. But if you are multiplying it by a number that's negative, obviously we know that having the negative of a vector means it changes its direction, so it'll be a vector going in the opposite direction. Right, okay, so just one last thing, which is to do with vectors for this one, which we should know, which is important, which is vectors are only equal if both the size of the magnitude and the direction are the same. So like vectors can be, like the magnitude can be the same, but if they're in different directions, it's not an equal vector. So it's very important to distinguish that between kind of speed and things. Things can have the same speed, but if they're going in completely opposite directions, then the vectors that are equivalent, the vectors aren't equal. The vectors will be different because their direction is different. Okay, this is all kind of review, so I'm not going to do any examples for this. If you need any examples, just let me know. Okay, so that's kind of the revision of vectors, so it's now going on to some new ways of working with vectors.